In this video, we are going to be looking at magnetism, final unit. So when it comes to magnetism, this is something you could do if you had a wire and a compass. But it turns out that if you run current through a wire, it can deflect a compass. And that tells us something really interesting. It tells us that current moving through a wire generates a magnetic field. And so what we want to do in this video is we want to look at two different kinds of magnetism. Ferromagnetism, which is the kind of magnetism that you just find in nature, a rock that has magnetic properties, right? That kind of thing. And then think about what magnetic fields look like, some of which you may already know. And then finally think about that very specific example of you run a current through a wire and you get a magnetic field. What does that look like and how can we use that? When it comes to electromagnetism, there are two things we need to think about. The first is the electric field, which we've already learned a lot about. And that is that charged particles create electric fields. The new thing is that moving charges create magnetic fields. And so all magnetism, as well as all electric effects, are directly or indirectly related to charge, and specifically for magnetism to charged particles that are moving. If they're still, they don't do this. So the big pieces today are how we create a magnetic field, and then how do we determine how strong that magnetic field is. The big ideas in magnetism are that you can put a force on a current carrying wire with a magnetic field, put a force on a moving charged particle, put torque on a coil or a magnet, cause it to rotate, which is interesting. Motors and generators are related to that idea. A changing magnetic field can create a current, and magnetic field is used in a circuit element called an inductor to deal with current flow. So what do we already know? Well, you probably already know that all magnets have two poles, a north and a south, likes repel, opposites attract. In that way, this is very similar to electricity, positive and negative. There are other things involved here, but things that are made of iron and a few other materials naturally occurring can be what we call ferromagnetic. Ferro, it comes from the same root that iron, ferrous materials. So we said before that all magnetism comes from moving particles, but a big horseshoe magnet doesn't seem to have moving charge, but it does. Electrons are charged and they are always moving. So the electron spin and the orbitals of it is what is happening inside to cause there to be a magnetic field. And inside we get what we call domains. In a standard unmagnetized hunk of iron, they would all sort of be pointing in random directions. But to magnetize that, align some of them so they're going in the same direction, and you get a net magnetic field. The magnetic field is given the symbol B for the magnetic field, not M, although you will sometimes see M. And so if you want to make a magnet, basically what you do is you take a hunk of metal and you put it in a magnetic field, and then you get the magnetic domains to align. Now, if you do this while the material is, say, molten and then cooling, you can kind of get it in its more flux state to set that way. But if you heat it up again or expose it to unaligned magnetic fields, you can cause it to, or hit it really hard, you can actually cause all this to go away. When it comes to the magnetic field, we map it using a compass. By convention, the magnetic field basically goes in the direction that the north points. So it goes out of the North Pole and into the South Pole. So the South Pole points toward another North Pole. That's on those little compasses. The red is the north, the white is the south. And so we draw something like this, out of the north and into the south. Unlike a dipole, although this looks a lot like a dipole from electricity, you have these continuous lines, which are similar, but you don't have the separate north and south. It turns out you cannot have just a south pole or a north pole. You always have both a north and a south. That's because it's the moving charge that generates this, not just a point charge. A bar magnet shows us a magnetic field that looks something like the one on the left. A horseshoe magnet is basically a bar bent around, so the magnetic field is really concentrated at the ends and then mostly traveling through the horseshoe instead of outside of it. The Earth has a magnetic field. This is based on the spin of the molten iron-rich core, not the spin of the Earth directly. But there's a spin axis and there's a magnetic axis, and they're not exactly the same. What we call a north pole of the Earth is actually the place the compass north points toward, which is actually the south pole of the Earth's magnet. And so this is, again, going back to that idea that this looks a lot like a dipole, but you'll notice that the magnetic field doesn't have a place that it actually starts and ends, unlike the electric field. The electric field starts on a negative, or starts on a positive, ends on a negative. It appears that magnetic field starts on north and ends on south, but what you'll find out is that it's actually continuous all the way through, even inside of the material, which is different from the way electric fields behave. So we want to talk about Gauss's law for magnetism. And basically, this is an idea of flux, right? So the magnetic flux through any Gaussian surface is always going to be zero. So if we were to try to apply the Gauss's law argument to magnetic fields, we would always have zero something enclosed, which is what we have. So this basically means that there's no such thing as a magnetic monopole, a north or a south pole by itself. This is pretty fundamental to the difference between electricity and magnetism and the way we understand the universe to behave. So electric currents creating B fields. Ørsted, who is Dutch, I think, was Dutch, something like that, demonstrated this for the first time and to, a crowd of onlookers. And this was really important because up to this point, we knew about magnetic fields. We knew how to sort of use them to navigate with a compass, but this allowed us to create magnetic fields in a controlled way. The direction of the magnetic field follows what we call the right-hand rule, or one of the many right-hand rules. The magnetic field is always perpendicular to the current and going in a circular path. So basically, you stick your thumb in the direction of the current and your fingers wrap around that. You could also use something like a pencil, call the lead of the pencil the direction of the current, put your thumb that way, and then it wraps around the pencil. So that's, sometimes we call this the little right-hand rule because it's just two things, a magnetic field and a current, relatively straightforward, a bunch of circles. When we use the right-hand rule, we do it kind of like this, a bunch of different diagrams for you. But this is a little bit hard to draw, drawing these 3D diagrams all the time on a 2D piece of paper. I'm not very good at drawing them. These are all, stolen from places on the internet. People generated them. So what we do is we say that if you draw a dot, then that's something coming out of the page at you, right? So if this is a wire coming out of the page at you, you could, take your pencil and point it towards yourself and say, okay, my thumb is that way. Which does the current, way does the current go? And it would go counterclockwise in this case, right? Around that current coming out at you. So that's one thing we can do. What if it's going in the plane of the page? Well, then it comes out at you at the top and goes in at the bottom. And so what we use is dots for coming out of the page and X's for going into the page. And the best way to think about this is that if you imagine a little arrow or dart with little feathers on the end, when it first pokes out of the page at you, you would just see a little dot from the beginning of the arrowhead. But if it were going away from you into the page, you would see the little X of the feathers, or the fletching, I think it's called, on an arrow, going away from you into the X. So that's the convention. You just kind of have to memorize it. Out is dots, in is X's. So that's the way we think of our directions when we're drawing something that's really three-dimensional in the plane of a page, right? Anything that's in the plane, you can draw as arrows or circles. Anything coming into or out of the page, we use these X's and dots. All right. So that is your introduction to magnetism, right? Moving charge generates magnetic fields with a direction determined by the right-hand rule. We have some conventions for how we draw that, but that's